we start with the final stages. The final stages of the sun. Alright? To recap, আমরা কি পড়তেছি? Remember last class we studied that a star can have mainly two life cycles. It can either have if it is a small like average star like our sun for example, then it will follow this life cycle from nebula to average star to red giant to planetary nebula to white dwarf. And if the star is much bigger, by bigger I mean much more massive, so if the star is much more massive than the sun, in that case it will follow this life cycle: massive star to red supergiant, I mean starting from nebula again, starting from nebula to massive star to red supergiant to supernova, and then to either a neutron star or a black hole. Okay, so we are studying the first one. From average star it will become a red giant. Up to this we covered in last class how it turns from an average star to a red giant. Today we're going to talk about the rest of it, red giant to white dwarf. So let's just get into it. Okay. Most of you are probably joined. I should continue. Okay. Okay. So like I said, the final stages. So we studied up to red giant. Now what happens after red giant? Well, before we get into it, okay, like since we are also waiting for the others to join, let me recap a little bit more about what we studied last class. So how did the red giant form? Do you remember how the red giant was formed? You remember that? Because the red giant was formed because although the balance between the inward force of gravity and the outward force of radiation pressure in a main sequence star can allow the star to shine with a fairly constant output for over 7 billion years, the hydrogen fuel required for nuclear fusion will eventually run out, right? The hydrogen fuel will eventually run out. So when this happens, the core of the star begins to collapse, right? After the hydrogen fuel runs out, the core of the star begins to collapse, right? And when the core of the why does the core begin to collapse? Due to the relentless pull of gravity, right? Then this increases the temperature of the star, right? Since the star becomes as the star collapses, it increases its temperature because all of that energy is now in a smaller space than before, as it is now in a smaller space. Yes, walaikum assalam. And as it is in a smaller space and the temperature has increased, so the pressure at the core of the star will also increase. So as the core of the star, this is talking about the main sequence star, right? The main sequence star. So as the core of the star begins to collapse due to gravity, I'm highlighting the keywords for you. Okay, I'm highlighting the keywords for you so that you can remember. When the main sequence star, basically when its hydrogen fuel runs out, basically which is required for nuclear fusion, right? Hydrogen fuel which is required for nuclear fusion runs out. When this happens, the core of the star, you have to remember this, the core of the star begins to collapse. And due to what? Begins to collapse due to gravity. And as the core collapses, what happens? This increases. What does it increase? The temperature of the star and the pressure of the star. Where does the temperature and pressure increase? At the core of the star. Okay, so as there is more and more temperature and pressure, so what will happen if temperature and pressure both increase? What will happen? The star will now start fusing helium. in its core to produce more energy and more radiation pressure, right? More energy and more radiation pressure, because the star now produces more energy because it is now fusing helium. Previously, in the when it was in the when it was a main sequence star, it was fusing hydrogen, but now it is fusing helium. So obviously, the nuclear fusion of helium releases much more energy than the nuclear fusion of hydrogen, correct? So as the nuclear fusion of helium releases way more energy, what happens? Pushes out the outer layers of the star, right? The radiation pressure basically pushes out the star. Okay, so what happens? Let me just highlight part of it. The radiation pressure pushes out. So as the radiation pressure pushes out, what will happen? The star basically swells up. Okay, the star swells up dramatically. So basically, this just means that the star becomes very large, and as it becomes very large, if you remember, as it becomes very large, they cool down, right? As the star becomes very large, and now the outer layers are far away from the from the core, so the surface of the star. When we are talking about they, we are talking about the surface of the star. Okay, the surface of the star. When I say they, I mean the surface of the star, right? So the surface of the star basically starts to cool down, and as the surface cools down, and only glow with a red color, because when something cools down, when a star's surface cools down, its color changes, remember? Because why does its color change? Because as we know, um, the color of a star depends on the surface temperature of the star, right? The color of a star depends on the surface temperature. So as the and we have studied this before. If you can recall this chart, you recall this chart, right? The color of the star, like when it is yellow, the sun is normally yellow, so that's a 6000 Kelvin surface temperature. But it becomes orange to red is only 2400 Kelvin temperature. Or as I showed you in my slide, this color chart, right? That is why a red giant is red, because it has a lower surface temperature. A red giant is red because it has a lower surface temperature. Okay, anyway, moving on. Now, that was up to last class. That was just a quick recap. Okay. Acha. Um, Although you might expect larger stars to last longer, the lifetimes of the most massive stars are among the shortest. Let me highlight this. This is also important. The lifetimes of the most massive stars are actually the shortest. This may seem counterintuitive. You may expect that, okay, the sun is a small star, it will last about 5 billion years. So maybe a huge, massive star will last longer. But actually, it's the opposite. Actually, it is the opposite. Okay? So the massive stars, the big stars that are much more massive than the sun, they actually have short half lives. Their lifetimes are actually the shortest. The most massive stars actually have the shortest lives. And by life, I mean basically the main sequence stage, because that is the most stable state of a star. So when we are talking about the life of a star, we are mainly talking about the main sequence phase. Okay. Although they were formed from a larger nebula, the inward gravitational forces are much stronger, forcing them to burn their hydrogen fuel much more quickly. You understand now why this is the case? So, the lifetime of the massive stars is the shortest. Why? Because their inward gravitational forces are much stronger, right? Because they have larger mass, so they have higher gravitational forces. So they actually burn or fuse rather. By burn, burn means basically fuse. Here burn means fusion, nuclear fusion. Burn means fusion, okay? So they burn their hydrogen fuel much more quickly. Much more quickly. You understand? You remember main sequence Konta? Main sequence stars are those. Main sequence stars is a stable star. Stable star is the main sequence star. When do we call a star main sequence star? When the radiation pressure is strong enough to balance the gravitational forces. So the keyword is actually just this radiation pressure. When radiation pressure balances the gravitational force, then that star is a stable star is formed, and that stable star is called a main sequence star. And the star lasts in this main sequence phase for a very long amount of time, and then after that main sequence phase the star becomes a red giant in case of um, small average stars. Anyway, so from nebula we get the protostar to stable main sequence star. Okay, now like I was saying, lifetimes of most massive stars are the shortest. The inward gravitational forces are much more stronger, so they burn their hydrogen fuel more quickly. That is, they fuse their hydrogen more quickly. Is that clear? Okay. This is the Orion constellation, like I told you before. Okay, let me just go back to the slide here. Yeah. Okay. So, like I said, the helium fusion releases a lot of energy, so it becomes a red giant. What happens after the star becomes a red giant? What happens after the star becomes a red giant? Everything that I'm showing you guys will be given to you as PDFs. Not will be, actually has already been given to you as PDF in your group. Please check your group. There I gave two PDFs, topic guide astrophysics and slide 2. This is slide 2. I gave this whole PDF, and also topic guide astrophysics. Please find it in your group. Okay, moving on. Now, after what happens after red giant? You may ask, what happens after red giant? Now, that after red giant is the final stages. So, you need to remember what was the nuclear fusion going on in main sequence star. In the main sequence star, what was the nuclear fusion? Hydrogen fusion. You remember that the the fuel was hydrogen in main sequence star. The fuel was hydrogen, and the byproduct was helium. Right? You need to remember this. In main sequence star, you need to very clearly remember this. In main sequence star, the byproduct is helium, and the fuel is hydrogen. That is the nuclear fusion is occurring of hydrogen. So hydrogen fusion is occurring in main sequence star, and it is producing more and more helium. Example I can give, example you can Google. I don't, star names are not that important to me, at least. Anyway, um, so example of a red giant star is our sun 5 billion years later. Okay. Anyway, So the fuel is hydrogen. So in a main sequence star, the fuel is hydrogen and the byproduct is helium. So hydrogen is fusing and helium is being produced. Now, what about in the red giant? In the red giant, the helium is the fuel. Helium is the fuel, right? So in a red giant, helium is being burnt and burnt and burnt, as in fused and fused and fused. Helium nuclei are fusing. But what happens when most of the helium nuclei have fused together? When most of the helium nuclei have fused together. Uh, so when most of the helium nuclei have fused together, uh, please do not make unnecessary comments in the live chat. Only ask your questions. Anyway, so when most of the helium nuclei have fused together, an explosion can occur that throws some material from the star into space, forming a planetary nebula. Alright? So, why? Why may this occur? I think I should put this point at first. Yeah, yeah, okay. So, as the fuel, what's the fuel in a red giant? Helium. As a fuel, helium, to produce energy to support the red giant star runs out, the outward pressure from fusion drops. Outward pressure meaning radiation pressure. Okay, the outward radiation pressure from fusion drops, and gravity takes hold. By takes hold, I mean becomes dominant. Gravity becomes dominant. Obviously, just like in the main sequence to red giant. How did this occur? How did the sun become a red giant? You remember? Hydrogen was the fuel. Hydrogen was the fuel, and it was burning that hydrogen. But when that hydrogen was almost all burnt up, almost over, what happened? The star started to collapse due to gravity, because the outward radiation pressure decreased, but so gravity became more dominant. Similarly here fuel is helium. So as the helium is running out, so the star cannot produce as much energy as before, right? I will explain the planetary nebula in a second. The fuel helium runs out, obviously less and less nuclear fusion occurs, right? So as less nuclear fusion occurs, so the there is not enough energy to support the red giant star. That is, the outward radiation pressure now decreases, drops, right, or decreases, and so gravity becomes dominant, correct? So causing the star to contract to a much smaller size. Let me summarize this here. Like, fuel helium um, runs out, and then what happens? That is, decreases. So radiation pressure also, like, so radiation pressure also decreases, correct? So what happens if radiation pressure decreases? If radiation pressure decreases, gravity is now greater than radiation pressure, right? So what will happen if gravity is greater than radiation pressure? The star will contract, meaning compress. Okay, so the star will contract. Hope that makes sense. Okay, Now let me just hold on a second. Let me just read from here now. So eventually the thin outer layers of a red giant star will run out of energy. Like we are saying, right? The helium is running out of energy. The helium fusion is not occurring, so the star is basically running out of energy. And only the core of the star will remain. Okay? So what happens is, in the red giant star, what happens is, the byproduct from helium, PDF minor additions you can note down in your copy, or I will give you the edited version again as PDF. But like, I'm gonna I will save the edits from today, but I did not save the edits of previous classes, so it would have been better if you noted it down, but I'm saving it as topic guide edited, and I will give you the edited PDF as well. That is the highlighted, okay? Just note down the highlighted words, that will be better for you to remember. If you note down the highlighted words, it will be easier for you to recall. Okay, now, like I said, when most of the helium have fused together, right? Now, what happened? Now, I'm again gonna go back to main sequence star. What happened in main sequence star? In main sequence star, the hydrogen run out, right? And then the star contracts. But when the star contracts, something happened in the main sequence star. Remember that? What happened when the star contracted? The helium started to fuse. So helium fusion started, correct? However, in the red giant, it doesn't contract that much. The mass is not enough to cause the next stage of fusion. That is, after hydrogen fusion, helium fusion. Now helium produces lithium, and mainly lithium. Helium mainly produces lithium by fusion, right? Helium mainly produces lithium by fusion. So when helium actually produces lithium by fusion, now if the star again wants to burn something, it has run out of helium, right? What does it have now? What's the core of the star? The core of the star now has the byproduct of helium, right? The byproduct of helium. So the byproduct of helium is lithium. Now, lithium fusion cannot occur in these stars because these are small stars. Their mass is not large enough to cause the next stage of fusion. Okay? Okay? The mass of the star is not large enough to cause the next stage of fusion by this contraction. Okay, this contraction does not trigger to trigger, I'll say trigger. So this contraction, it does contract, but this contraction is not enough to trigger the next stage of fusion. And if fusion is over, if the star cannot fuse anymore, if the star cannot fuse its nuclei anymore, then what will happen? Then the star will actually die. This is the point in life cycle of a star where the star actually starts to die. Okay, so what happens here? When most of the helium nuclei have fused together, so like most of the helium nuclei have fused together, meaning most of the fuel has run out, right? So there is not much fusion to occur anymore. Now what happens is a slight explosion can occur. Okay, and that explosion, what it does is it throws some material from the star out into space. Okay, so it throws some material from the star out into space like this. You see this diagram here? So from the star it actually throws some of its material out into space randomly. So it just kind of explodes. Okay, it contracts and then it explodes. So when it explodes, sorry, let me just fix this for a second. Yeah. Now, now when it explodes, when the star explodes, it forms this shape and throws some material randomly out of the star into the space. It actually forms a planetary nebula. So this, you see those what can I say? Those wrinkles and dots all around the small ball. Those are no white dwarf and dwarf planet are completely different things. Just hold on a second. So anyway, so white dwarf and dwarf planets are completely different. Dwarf planets are, if you remember from slide one, please go check the first video. In slide one, we talked about this. Dwarf planets are the planets after Pluto. After Pluto, there is a belt. Sorry, not after Pluto. Pluto is a dwarf planet. There is a belt of planets after what's this? Saturn, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Sorry. After Neptune, there is a belt, and that belt consists of dwarf planets. Okay, it's called the Kuiper belt, and one of those dwarf planets is Pluto. White dwarf is a completely different thing. White dwarf is the end of a star. Now let's get back to the explosion now. Okay, we're talking about the star's explosion. So why this explosion occurs? Well, this explosion occurs because, you see, there is a large amount of there was a large amount of energy being produced by the nuclear fusion, right? But now that the star contracts, of course it cannot fuse the the next stage, that is lithium fusion cannot occur. However, as the star contracts, you see, the gravitational force of attraction is now higher, so the temperature and pressure actually increases. Not alien belt, I said Kuiper belt. Okay. Anyway, please let's focus on this topic now. Um, what was I saying? Something about physics. Um, okay, seriously, what was I saying? Planetary nebula. Yes, why the explosion occurs. So basically, as a star contracts really fast, as the star contracts really fast, because its fuel has mostly run out, the remaining parts of its fuel actually burns very quickly. All right. So as the remaining parts burn very quickly, so that releases a lot of energy, and that energy actually causes the star to kind of explode. It's not a huge explosion like supernova that we will study later. It's not a supernova, it's just a planetary nebula. A planetary nebula, if you look it up in Wikipedia, it will say just some radiation out of a star. Okay, some radiation. It's not a huge explosion. Okay, compared to a supernova, it's not a supernova. It's just a small explosion at the end of the life cycle of a small star, average size star. By the way, when I say small, of course I'm talking about, again, astrophysics scale. Okay, you have to remember the scale. Anyway, so now that explosion throws out some particles. So you can see the ball is very small here, right? You see a small little ball there, a pink one, right? So the rest of it is what? The remnants. That is the planetary nebula. Basically, it's called a planetary nebula, but it has nothing to do with planets. Okay, it's actually just throwed out material from the star. Okay, my guess will be that since planets are also ultimately throwed out materials from the star, because that's how planets are formed in the protostar phase. Maybe that's why they decided to call it a planetary nebula, but that's just my guess. Anyway, so this is the thrown out material from the star, causing the star to form a planetary nebula. And after the star forms a planetary nebula, what remains is this: a white dwarf. A white dwarf. That is, the star is dead. No more nuclear fusion. Just whatever nuclear fusion reactions the star went through during its lifetime, it is now radiating that energy in the form of light, but no more nuclear fusion is occurring in the star. Okay, so it's a white dwarf. Now you may ask, why is it white? It was red previously before, and if you remember from the temperature chart, red is at the bottom and white is at the top. Like what? Like blue, white. White is around the top, right? White. White is at the top and red is at the bottom. So white is a very high temperature compared to red. So how did the temperature increase? How did the surface temperature increase? Well, surface temperature increased because the star has contracted, right? Because it is now a very small star compared to what it was before. So it has contracted. So this contraction causes an increase in temperature. We have studied this before also. Contraction always causes an increase in temperature, right? The smaller a star gets, there is now more energy packed into a smaller space, so it's more dense, more temperature. Okay, so as it is very small now, it has contracted, but it still has some, it still has a lot of energy from the nuclear fusion reactions that it had in the during its lifetime. Due to those energy, it is still radiating as white light. Okay, it the star now emits blue and white light, mostly white and some slight blue, because as you can remember, the high temperatures are white or blue white, right? White and blue white are the high temperatures. Okay, now that's planetary nebula. So that's white dwarf. Okay, now, okay, before I get to the next point, let me go to your reading material one more time. So what is a white dwarf star? Do you have questions? Cold black dwarf star. Yeah, I'll come to that. Just whatever. So how the color is formed in the rims of the planetary nebula? Planetary nebula releases energy, just like any other star releases energy. So a star actually produces all sorts of colors, but we see stars as a particular color because that color is more dominant, like the star is emitting more of that color. For example, our sun is yellow. It doesn't mean that our sun only emits yellow color. Our sun actually emits all colors, but it emits more yellow than the other colors. The intensity of yellow light is more from the sun, so that is why it's a yellow. From a red giant, the more intense light is red. But when it's a planetary nebula, it's a it's quite messy, right? So some parts of it, it's just thrown out material from the star, right? So some parts of it are kind of cold, so those parts appear red, some parts appear green, some parts appear blue. It just different colors depending on different temperatures. That is why the rims of the planetary nebula have so many different colors. Okay, okay. Is the white dwarf made of lithium? Yes, the white dwarf is made of the byproducts of the helium fusion. So it's not only lithium, there is some lithium, there is some carbon, the byproducts of the star. Whatever nuclear fusion reactions the star was having till the end of its life cycle, the product of those nuclear fusion reactions forms the core white dwarf. Is purple hot or cold? If you look at the electromagnetic spectrum, purple is basically near violet, so it's pretty hot. The more energetic, the higher frequency in the electromagnetic spectrum. Okay, now uh, let's dive a little deep in about white dwarf stars. Okay, so eventually, like I'm repeating what I just said there, eventually the thin outer layers of a red giant star will run out of energy, we know that, and only the core of the star will remain. This is important. What will remain? Only the core. Only the core of the star will remain. Right? Only the core. Because the rest of it has been thrown out into space as a planetary nebula, right? So this core is called a white dwarf star. Now, what is a white dwarf star? It is the hot, dense core of a star which has passed through the red giant stage. It is the hot, dense core of a star which has passed through the red giant stage. That's a white dwarf star. Okay? I hope it's clear so far. Now, here's the surprising part. When the sun, and we know how big the sun is, right? It's 99% of the mass of the solar system, and Earth is not the biggest planet in the solar system, not even the biggest planet, but all the other planets and Earth and everything else makes up 1% of the mass of the solar system, and the sun is 99% mass of the solar system. So the sun is huge compared to the Earth. Correct? Correct. Now, when the sun becomes a white dwarf star, it is expected to be only about the size of the Earth. Just think of how crazy this is. The sun, this huge sun, the size of the Earth. Okay? Now think about the mass of a star. Right? The sun had a huge mass compared to the Earth, right? I wrote that mass before in your class. In your last class, I wrote that mass. What was the mass? 2 into 10 to the power 30 kg is the mass of our sun. In comparison, the mass of the Earth is 6 into 10 to the power 24 kg. Okay, so the sun is 10 to the power what's 32 minus 24? 8. 10 to the power 8 times. 10 to the power 8 means 100 million. The sun is 100 million times more massive than the Earth. Okay, so we know how the size of the Earth is. Okay, now imagine 100 million times the mass, but in the same space. The mass of a star, gravity has squeezed into a space about the size of a small planet. What will be the result? If the huge mass of the star, gravity squeezes it into a space about the size of a small planet, obviously that will be extremely, obviously is, it will be extremely dense. You understand what I'm saying? Alright? Like, think about it like this. Um, you take a bowl of, I don't know, cotton. You take a bowl of cotton, okay? And then you try to push it and squash it into a smaller and smaller space. You can squash it into quite a small space, right? But can you squash it into a space 100 million times smaller than its original space? I hope you cannot, because you're not Superman or something. So the gravity basically squashes and squeezes the whole star, the core of the star, because the core of the star has most of its mass, right? So it's almost the mass of the star squeezed into the space about the size of a small planet. So it is extremely dense. It is very, very dense. White dwarf stars are actually the are actually, I was about to say the most dense, but then I realized something. We are gonna talk about neutron star today as well. So no, not yet, not so fast. So white dwarf stars are one of the most dense objects in the universe. One of the most dense objects, okay? Alright. Now I'll go to black dwarf in a minute, but I want to say one more thing about this density. So white dwarf stars are made of matter that is millions of times. We know this, right? We just heard it 100 million times. So millions of times more dense than any matter found on Earth. Oh, I did not write this here either. Okay, I'll write it here. Why is that? My question is, why is white dwarf star so dense? Why? Because why is always the best question to ask. Okay, so why is the white dwarf star so dense? The answer is white dwarf stars are composed of nuclei only. Or I think I should say mostly nuclei only, but or I can say nuclei only. So white dwarf stars are composed of mostly nuclei only. You understand why? Because you remember, think about the atom. The atom is actually mostly empty space. You will, I don't know if you studied this in chemistry. If you did not, we will study this in radioactivity chapter of physics. The atom is actually mostly empty space. The nucleus of an atom is million times smaller than the atom itself. Okay, so if you took a tennis ball, sorry, if you took the entire earth and said, give me one, take away everything from the earth and just leave all the nuclei of the atoms, the earth will fit, the earth and all of its contents, us and everything, will fit into the size of a tennis ball. You heard me right. Tennis ball. The earth will, with all of its contents, if I just removed the empty space and put all the nuclei together, only the nuclei, then it will be the size of a tennis ball. And obviously, that will be millions of times more dense. You understand why? Because all of the empty space has gone, right? Like when I gave you the example about squashing cotton. If you take a lot of cotton and then you squash it and squash it and squash it, what happens? How are you reducing its size? You're basically removing the empty space, the removing the air inside it, right? As you're squashing the cotton, basically air is getting removed from it. So empty space is getting removed. Similarly, from an atom, if you take out the empty space, if you just keep the nuclei, and if you only keep the nuclei from everything else, you're left with just the nuclei. The space occupied will be millions of times smaller, and so the density will be millions of times higher. And since white dwarf stars are composed mostly of nuclei only, so they are millions of times more dense than any matter found on Earth. Hope that answers the why question. Okay. Um, The sun is. Okay, so how does? Okay, now that we know how dense, let's move on to cold black dwarf. Well, what happens is basically the white dwarf star. It used to be in the good old days, in its golden ages. It used to be a main sequence star. It used to be a stable star. It had a good life. It produced a lot of energy by nuclear fusion of hydrogen atoms, hydrogen nuclei, right? Nuclear fusion of hydrogen and made it release a lot of energy, right? And it produced a lot of energy. And also, then in its not so golden days, but still in the red giant phase, it burned some helium and produced a lot of energy there too. So, in the old age of white dwarf, it does not have any nuclear fusion to carry out anymore. It doesn't carry out any more nuclear fusion. It just emits light from the energy that it had previously produced, right? But that energy, as it is continuously being radiated to the surroundings, as the energy is continuously being given away to the surroundings, the energy will eventually run out, right? Because now the star is continuously glowing because it is continuously emitting energy and producing more energy by nuclear fusion. It is producing more energy and emitting more energy, right? But the white dwarf star, if you think about it, it doesn't produce energy anymore. However, it is still radiating energy, right? It is still radiating energy, but it does not produce energy anymore. So as it does not produce energy anymore, so its temperature starts to fall. Okay, so as its temperature starts to fall, it starts to lose its white color, right? Because it cannot radiate enough energy to maintain a white color yet. Because white, to maintain white, the temperature needs to be very high, so it needs to radiate a lot of energy. As the energy runs out, it starts to become a brown dwarf that is in the red end, like its color deteriorates to red, brownish, and eventually it runs out of all of its energy and it becomes a cold black dwarf star. And actually, it's no longer a star because it is not anymore producing any light or any energy. It is not emitting energy. It is not emitting any light. We cannot even see it. It's just there. It's just there. It just lies around in empty space as a cold black dwarf star. And that is the future fate of that has been the future fate of all stars that were the mass of the sun. So we astrophysics students and astrophysicists predict that that must be also the ultimate fate of the sun. It will turn into a red giant when the hydrogen is when it runs out of hydrogen. Then it will turn into a helium when it runs out, and then when it runs out, then it will turn into a red giant, and then when it runs out of helium, it will, for a small amount of time, become a planetary nebula, radiate a lot of energy, and then become a white dwarf and continue to radiate energy, and slowly but surely its temperature will decrease and decrease until it becomes a cold black dwarf star. This is a very slow process. Very slowly the white dwarf star will cool and dim. As it becomes cool, its temperature falls and also it becomes more and more dim, and it finally becomes a black dwarf star, marking the end of its evolution. That's the end of the life cycle of an average star. This is where the life cycle of an average star ends. Okay? So, any question thus far? all the nucleus in the Earth can fit in a tennis ball. Yes. So it is now a rock. Well, yeah, kind of. It is now not really a rock. I wouldn't say rock because it's still a ball of gas, but it's just not emitting any more light, and no longer any fusion reaction, and also it's a ball of gas, not even gas. It's a ball of nuclei. Okay, it's a ball of nuclei, so much more different than a rock because it's, like I said, millions of times more dense than anything found on Earth. So, but it's just a cold black dwarf star. Yeah. There is no catalyst here. This is the fate of our sun. Like, that's what our study tells us so far, at least. Okay. So if you don't have any questions, we're gonna move on to the big guns, the big guys. Okay, what's another question? So in the phase of planetary nebula, does it help to create planet? Create planet? No. In the it's a planetary nebula is the star throwing out its materials and becoming a white dwarf star. So it contributes to other nebula from which a star can form, and then maybe from that star planets can form. That's a different story, but directly saying planetary nebula gives birth to planets is not really correct. um well you're saying that black dwarf can be a mine for lithium and we can mine. First of all we cannot even explore the entire solar system. So good luck getting out of the solar system first and reaching the nearest star, which is also not a cold black dwarf. And also, first of all, good luck finding a cold black dwarf star because it does not emit any light. So how are you even gonna find a cold black dwarf in empty space? And even let's just assume that you go there all the way, fine, everything works out. Even then, it's all nuclei. It's all lithium and carbon nuclei, not lithium atoms. It's all nuclei. It's a ball of nuclei. So it's completely different. Does a black dwarf consist of mostly nuclei? Yes, mostly nuclei. Imagine, yeah, I imagined a lot of things and then still just told you, like, you will still find just a ball of nuclei. So, can I be possible? Can you be possible? I think you are pretty possible. Otherwise, you wouldn't be commenting here. Okay. Now, moving on from the question answer session, we're moving on to the more massive stars. Okay. So when I say more massive stars, I mean life cycle of stars that are much larger than the sun. Okay, much larger than the sun, much more massive than the sun. So we started this one: average nebula to average star to red giant to planetary nebula to white dwarf. Now we are studying this one: massive star to red supergiant to supernova to neutron star or black hole. Okay, so life cycle of stars much larger than the sun. What happens here? Well, after the stable period, after the stable period, these stars contract. Okay, so the life cycle of these stars, up to this point, they are identical. From nebula to main sequence, or from nebula to main sequence star, or from nebula to stable stars. The only difference is from small nebula, average or small stars are formed. From large nebula, massive stars are formed. Cool? Okay. Now, after the stable period, that is after the main sequence period, What happens in normal star? In average star, what happened? Remember? The hydrogen was running out, right? So these stars also contract, fine. However, these stars contract with energy high enough to cause further fusion beyond lithium, okay, which makes the outward kinetic energy dominant, that is outward radiation pressure dominant over the gravitational attraction, and the star expands into a large red supergiant or blue supergiant. Let me explain what I just said from a little bit more from the reading material. Uh, uh, okay, there's not much information here, so since there's not much information here, so let me just go back to the slide again. I'll get back to that Indian astrophysicist. Don't worry about it. We'll talk about him. Okay, so let me clarify this again. After the stable period, what's supposed to happen after the stable period? Well, after the stable period, hydrogen is gonna run out, and then it's gonna form the star is gonna contract, and when the star contracts, helium will start to fuse, and as helium starts to fuse, there will be an expansion, large expansion, so it will become a red giant, and then once the helium runs out, the red giant is gonna contract, and then what happened in the average star? When the red giant started to contract, in the average star, when the red giant started to contract, we saw that the star collapsed into a white dwarf. Going through a planetary nebula, it eventually became a white dwarf. But when the stars are much larger than the sun, that is, when the stars are massive, they have so high gravitational force that whenever they contract, every time the gravitational pull and the kinetic energy and the temperature and pressure increases to such high values that always the next stage of fusion is possible. Every time the next stage of fusion is possible. So what happens after the stable period? These stars contract with energy high enough to cause further fusion beyond lithium. Okay, now, okay, let me just make this a separate point. So far so good that beyond lithium. All right, let me make the font a little bit bigger. Yeah, okay. So far so good that after the stable period, these stars contract with energy high enough to cause further fusion beyond lithium. Normal stars, average stars could not cause the fusion of lithium because the fusion of lithium required so much high temperature and pressure, and that much high temperature and pressure did not occur in those stars, but in the stars that are much more massive. Let me clarify this even more if possible. As these stars are more massive, they have greater gravitational force, so when they contract, much higher temperature and pressure is produced. You with me so far? As these stars are more massive, so they have greater gravitational force, right? I'll make some things bold. More massive, so they have greater gravitational force, so when they contract, much higher temperature and pressure is produced, right? And since the temperature and pressure is much higher, Therefore, the next stage of fusion beyond lithium is produced. Sorry, the next stage of fusion beyond lithium, I'll say next stages, plural. The next stages of fusion beyond lithium are also triggered. Okay, so after the stable period, these stars contract with high energy high enough to cause further fusion beyond lithium. Why? Because as these stars are more massive, they have greater gravitational force. So when they contract, much higher temperature and pressure is produced. Therefore, the next stage of the fusion beyond lithium are always triggered, are also triggered, right? Now, I want you to again recall. Do you remember? I know, I know, we're studying a lot of things. It's difficult to remember. Just bear with me a little bit. Do you remember how the big stars, sorry, the average stars, um, okay, what was I saying? Yeah, sorry. Yeah, so you remember helium fusion releases more energy than hydrogen fusion, right? Helium fusion releases more energy than hydrogen fusion. Similarly, lithium fusion will release more energy than helium fusion, right? Because the heavier the nucleus, the bigger its fusion reaction. So it releases more and more energy. Okay? So in these stars, as next stages of fusion beyond lithium are also triggered, the outward pressure, radiation pressure, becomes dominant over the gravitational attraction. So the outward radiation pressure becomes very very large because because like I said, nuclear energy is much more. So radiation pressure becomes dominant over the gravitational attraction. And as radiation pressure becomes more dominant over the gravitational attraction, the star expands into a large red supergiant or blue supergiant. Okay, let's just stick to red supergiant. There is some confusion regarding blue supergiant. And blue supergiant can be like this, or they can also be maybe from main sequence. Like there's some confusion there. I'll skip it. Also, it's not in your syllabus, so I'll skip it. So the outward radiation pressure becomes dominant over the gravitational attraction, and the star expands into a large red supergiant. Obviously, red supergiant. You get the point, right? Bigger than the red giant, red supergiant. Simple. Okay. Okay. Now, once a star becomes a supergiant, it cannot become a white dwarf again. Okay, it can never become a white dwarf again. I will go ahead and say it can never become a white dwarf again. Why? So, once a star becomes a supergiant, can never become a white dwarf again. Remember this. Why? Because these are so large that the kinetic energy during collapsing, or I will rather say that the increase in temperature and pressure, because yes, kinetic energy is high, but the main point is temperature and pressure. So because these are so large that the increase in temperature and pressure during collapsing, is always enough to to trigger the next stage of fusion. Okay, so because these are so large that the increase in temperature and pressure during collapsing is always enough to trigger the next stage of fusion, and then the next stage of fusion, and the next. So it's like in these supergiants. Here's how it works. I'm again gonna recap what happened in the normal average star. What happened in the normal average star? Main sequence, hydrogen fusion. Hydrogen runs out, star contracts, helium fusion starts, star blows up, becomes big, becomes red giant, hydrogen fusion continues, and then once hydrogen fusion is over, sorry, helium fusion continues, and once helium runs out, the red giant collapses and becomes a white dwarf. End of story. Why collapse? Because white dwarf could not trigger. Now what happens in these massive stars? Main sequence, hydrogen fusion, contracts, helium fusion, and beyond helium, lithium fusion, because the contraction is so large. So huge amount of energy released, so it becomes not just red giant, becomes red supergiant. Now what happens to the red supergiant? Lithium fusion occurs, lithium runs out, star begins to contract. Just after a little bit of contraction, carbon fusion starts. Carbon fusion continues. Carbon fusion continues. Carbon runs out. Little bit of contraction. Little bit of contraction. What's the next element after carbon? Oxygen, I think. Oxygen fusion starts. Oxygen runs out. Star contracts. And then again, what? I'll go to the periodic table now. I don't remember. So sorry, beryllium fusion occurs. Okay, lithium after lithium, beryllium fusion. After beryllium, boron fusion. After boron, carbon fusion. After carbon, nitrogen. Then oxygen. Then fluorine. Then neon. Then sodium, magnesium, aluminium, silicon, phosphorus. You get what I'm saying? Every element of the periodic table. So the core continuously causes one fusion, produces another element. Then when this element runs out, the fuel runs out, the core starts to collapse, and then again another fusion starts occurring. Then the next element is produced. Then the star again contracts. Then the next element is produced. Now, if you go in the periodic table, you will see aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, and then a lots of, okay, not really lots. I'll actually finish it. Potassium, calcium, Sc. I'm not sure what that is. I'm not sure what the next one. Titanium, vanadium, chromium, and then manganese, and then iron. So manganese fusion, chromium fusion occurs, and then the core becomes iron. Okay, so all elements in the okay, so sorry, we are not there yet. This is the next point actually. So eventually the core becomes iron, because every stage of fusion before iron has occurred. Okay, so any question so far up to iron? Any question? No, not uranium, not iron fusion. I'll get there. No, not yet. So any question up to iron? Okay. No, all your questions is iron fusion. Greater gravitational force cannot থাকে. Greater gravitational force because greater mass, more massive, so more gravitational force. What will happen? A red giant, red supergiant, it will never turn back into a white dwarf. Once I've said it in bold. Once a star becomes a supergiant, it can never become a white dwarf again. Never, not possible, impossible. Okay. Now, okay, iron core. Why does the core become iron? Because, like, let me repeat. When hydrogen fusion occurs, what does the core become? The core becomes helium. When helium fusion occurs, what does the core become? The core becomes lithium. When lithium fusion occurs, what does the core become? The core becomes beryllium, boron, carbon. When these fuse with each other, beryllium, boron, carbon, the core becomes nitrogen. Then the core becomes oxygen. Then fluorine, then neon. Then when fluorine, neon, these um, fuse with one another, then sodium, magnesium, then aluminium, silicon, then they fuse with each other, then phosphorus, sulfur, then they fuse with each other, then chlorine, argon, then they fuse with each other, then potassium, calcium, then they fuse with each other, then scandium, titanium, then they fuse with each other, then vanadium, chromium, then they fuse with each other, then vanadium, chromium, manganese, they fuse with each other, they produce iron. So up to this point, nuclear fusion has occurred, and iron has iron has been produced. Every element in the periodic table up to iron and before have been produced. So what will happen now? Obviously, our common sense tells us what? Iron fusion will occur, right? No, no, no. Iron fusion is impossible. Nuclear fusion of iron is impossible. Impossible in bold. Okay? Now you may ask why. You may ask the best question that human beings can ask. Why? Nuclear fusion of iron is impossible. Why? Because iron is the most stable nucleus. Among every other nucleus in the what can I say? Among every other nucleus in the universe, iron nucleus is the most stable nucleus. Now, of course, you can again ask why. Why iron nucleus is the most stable nucleus? Now I have to say that statement that you don't like that much, we will study in A levels. It has something to do with the term binding energy, and if you calculate the binding energy per nucleon value of all the elements in the periodic table, and you draw a curve of element versus binding energy on the y-axis and nucleus on the x-axis, you will see iron nucleus has the highest binding energy per nucleon value, and all other elements, all other nuclei have lower binding energy per nucleon value than iron. Okay? Alright. So now now the question comes, okay, up to iron everything is formed, but we see these other weird guys, uranium, gold, silver, copper, whatnot, right? Where did they come from? That's one question. And part 2 of the question, wait. Iron fusion cannot occur. So now the core is iron. Okay. Now the star will start to collapse again, right? Because once everything becomes iron, no more nuclear fusion. And no more nuclear fusion means what? No more radiation pressure. No more radiation pressure means what? The star will start to contract. The star will start to collapse, right? Yes, indeed. I will come to this point later. So after this, as red supergiants start to collapse, okay, so it's a huge star. It's one of the biggest stars in the universe. Okay, one of the biggest stars. There are lots of red supergiants, but yeah, these are the big guys. The big guy at its last stage, it has carried out all the nuclear fusions possible. Now there is no more, and it's starting to collapse. I love this part. The best thing occurs here. As the red supergiants start to collapse, the kinetic energy is so large. The kinetic energy is so large, and the temperature and pressure increases to such high values, because as the red supergiant collapse, it has huge mass, So huge gravitational energy, and it has been carrying out so many nuclear fusion reactions. So already the temperature and pressure is so high because so many nuclear fusion reactions have occurred. So very high temperature, lot of energy. It is starting to collapse. It is starting to contract. There is so much energy that now iron nucleus cannot fuse, right? So what happens is the iron atoms, they still have electrons, right? Well, the electrons, oh my god, this part. The electrons are pushed into protons. Yes, you heard me right. Electrons are pushed into protons to form neutrons. Okay? So electron and proton are always repelling, right? No matter what, like there is always electrostatic repulsion. I mean, sorry, attraction. Electron and proton are always attracting, but the electron is always what? Orbiting the proton. It never comes near the proton. It never comes near the nucleus, right? But now the temperature and pressure is so large that the electrons are pushed into protons to form neutrons, and this is called subatomic particle fusion. This is called subatomic particle fusion because you know so far we had been studying what? Nuclear fusion, because it was two nuclei fused together to form a new nucleus. Now this is a proton and an electron. They are not nuclei, they are subatomic particles. These subatomic particles are boom boom fusing into one another to form neutrons, and this is called subatomic particle fusion. Okay, I'm gonna take this point to the last. So as subatomic particle fusion occurs, the energy released by this fusion is so large, like we cannot even imagine. Like, well, you can kind of imagine. Just think about it like this. Again, yeah, the nuclear bomb, Hiroshima, Nagasaki, huge energy, right? Hydrogen fusion in at the core of our star, many times more energy. Helium fusion at the core of red giants, many times more energy. Now think about all the more fusion reactions. Manganese fusion, chromium fusion, the last stages of fusion, huge, insane amount of energy. Now think about iron fusion cannot even occur. But now think about subatomic particle fusion, when subatomic particles fuse into one another. This is the biggest amount of energy release in the universe. This is the highest amount of energy release. Like, if you call every star a power plant, this is the biggest power plant of the universe. It produces the biggest amount of energy. Okay? This subatomic particle fusion produces huge amount of energy, and the energy released is so large that the red supergiant now no longer expands, it explodes. And this is a real huge explosion, okay? This is a real huge explosion. The red supergiant explodes. And this process is called a supernova. This process is called a supernova, okay? This process is called a supernova. This huge explosion due to subatomic particle fusion, it is called a supernova. Alright, so now to come back to the to our question of, okay, up to iron everything was formed in the core of star, right, by nuclear fusion. Then how did the elements come after iron? Well, they come from supernova. They come from supernova. They come from due to the subatomic particle fusions. All right. So as the subatomic particles fuse into one another, neutrons are produced, more protons and neutrons are produced, and lots of different combinations are produced. So all the other elements in the periodic table after iron, all the elements beyond iron in the periodic table are only formed. Oh, sorry. All the elements that are beyond iron in the periodic table are only formed in supernova explosions. Okay? Alright? Now, what happens after supernova? Black hole and neutron star. We will study next class. Okay, any questions for this class? I'll end it here after answering your questions. Let's see. Um, okay, why in A levels? Say it now. There is no A levels. Why there is a ban A levels? What about okay, sir? How much time does it take for the stars to blow? The blowing stage, the supernova stage. I'm not exactly sure of the value, but a quick Google will let you know. Supernova lasts for how long does it? A few million years. Oh no! Sorry. Oh wow, this is amazing. Uh, a few million years. It takes a few million years for the star to die, but less than a quarter of a second for its core to collapse. A few hours for the shock wave to reach the surface of the star, a few months to brighten, and then a few years to fade away. Wow, this is amazing. I'm gonna add it to the slide just for curiosity. Okay, I'll add it here. Damn it. Yeah, okay. Oh, sorry, the font is too big. Oh, damn it. What is happening? Yeah. Sorry about that. Some technical issues. Okay, more technical issues. Fix it. Yeah, it's fixed. Okay, so it takes it takes less than quarter of a second. Less than. Oh wow. So less than 0.25 second. Quarter of a second you will have difficulty understanding. So I'll say 0.25 second. It takes less than 0.25 second for its core to collapse. So this subatomic particle fusion, 0.25 seconds. It takes a few hours for the shock wave to reach the surface of the star. So when the shock wave, that is the energy release, when the energy release reaches the surface of the star, that is when it will explode, right? Surface of the star. And then a few months to brighten, that is for a few months it it releases this huge extremely sorry guys, there was a technical issue. I think we're back. We will be back online very soon. Yes, we are back online. Sorry about the issue. Now, like I was saying, so it takes about a few hours for the shockwave to reach the surface, and a few months to brighten, and then just few years to fade away. So this huge explosion light only stays for a few years. Okay, a few years is a very short time in star life, by the way, because it takes a millions of years for a star to die. It lives for a billion years, for a few billion years, and then it dies for about a million years, like the red supergiant stage. That's also a few million years, and then just one or two few years to just fade away as a supernova. Now, instantly you say, okay, red supergiants become a hungry black hole, and the humble ones become a neutron star. Yeah, I'll talk about that. Yeah, black hole and neutron star next class. I knew that something will happen. Neutron. How is subatomic particle fusion possible? Yeah, it is possible. Hey, don't bam head on this stuff. Oh my god. So proton plus neutron electron equal to neutron. Only in subatomic particle fusion. It's not that simple in other cases. Okay. The brain is circling. I can't even imagine. Yeah. Oh, I like this. How do we know about the fusion stuff, especially the subatomic fusion? Surprise, surprise, we know all of this just from the light that we receive from the sun, light from that we receive from the stars. So from the stars, from the supernova, from the light that we receive, from its frequency, its wavelength, its speed, its angles, from all those informations we can calculate all of these things. How do you know the how Earth is made and from where all the elements from? I told you before in last class, remember? So Earth has all these elements. Why? Because it was made. It is a because it is made from sun, and the sun is a second generation star, right? So a second generation star is formed from a stellar nebula. The sun is actually formed from the stellar nebula of a supernova. Okay, so a supernova has all the elements, all the other elements in the periodic table, right? So because of subatomic particle fusion, so from all of those elements the sun was formed by, you know, just like nebula collapsing due to gravity. Okay, and then from the sun at its protostar phase, from parts of the sun, earth and the other planets were formed. That is why in the other planets we find all of these elements. ইলেকট্রন আর প্রোটন ফিউজ করে তো নিউট্রন গুলা কি হয়? আচ্ছা, নিউট্রন গুলা আইদার নিউট্রন স্টার হিসেবে থেকে যায় অর নিউট্রন গুলা ফর্ম করে ব্ল্যাক হোল। উইল স্টার্ট দিস ইন নেক্সট ক্লাস। ব্ল্যাক হোলে I will not finish this today. I'll leave that for teensy little bit for next class. Yeah, just for, you know, like teaser. Wow, now that is fast. Yeah, it's really it's incredibly fast. How have we calculated? I want my answers. Well, we calculated from all the different frequencies and, like I said, frequencies, wavelengths, etc. We will study some parts of it in the next few classes. Very much interested for black hole and neutron star. Sir, can we make a subatomic bomb? Hey, don't try. Electron or proton ki pressure জন্য fuse করে না? Yes, due to the insanely high temperature and pressure. The kinetic energy is so large and the temperature and pressure increases to such high values that electrons are produced into protons. Okay? মার্স কি আর্থে যে এলিমেন্টস আছে সেগুলো থাকবে? হ্যাঁ, মার্সেও এইসব এলিমেন্টস আছে, all the planets এ এইগুলো থাকার কথা. So what comes after Googleanium? The last element? What? I'm not sure. What? The last element is Googleanium? Okay, yeah, OG. No, like these are the elements. The periodic table consists of the all the elements that we have discovered or theorized yet. So yeah, that's it. Okay. So that is it for this class. In the next class, we will study black hole and neutron star. Yes, proton plus electron equal to neutron. Neutron has zero charge. The charge actually matches like this, yes, but this is only for subatomic particle fusion. If you just normally take a proton and an electron, they will never fuse and cause and produce a neutron. You need this much high kinetic energy and temperature and pressure. Okay. No ognesium. I'm not sure what ognesium is. Ognesium is what? The last element? Yeah, of course. That's also formed in supernova. Every every element after iron is formed in supernova. Subatomic bomb exists, mesons. Yeah, you can look that up in YouTube. Yeah, there are quite a few like papers related to that. Alright, I hope I could transfer some of my knowledge into you, our brains, and that is it for today. Thank you. Allah Hafiz. I'm ending the live here. Bye bye. Tata.